Okay, there's a question about this lovely homework problem, which was to find the Christoffel symbols of this type for cylindrical polar coordinates. And note the one contravariant index on this. And you're given the definition of the Christoffel symbol this way. So, a little bit of calculus, but mostly what this is index juggling and understanding what this means. So we have the definition of a Christoffel symbol as these mixed derivatives of the metric. So the first thing we need to do is figure out what the metric is for cylindrical polar coordinates. So cylindrical polar coordinates, we have a metric tensor. Well, so it's orthogonal. Any orthogonal coordinate system, I get 6 for free. So only zeros along the non-zero along the diagonal. Along the diagonal, what I have are the scale factors, the things that we've been using in curvilinear coordinate calculus, squared. Right, so just along the diagonal, scale factor 1, 2, and 3, quantity squared. So for spherical or cylindrical polar coordinates, I have, we'll call them rho, theta, and z. You guys probably used phi because that's what I've been using all quarter. I don't know why I'm changing the notation on you now, but there it is. Our theta, rho, theta, z. What is the scale factor for rho? It's already in units of distance, so that's 1 squared, or 1. What's the scale factor for theta? In order to turn that into an actual distance, a little bit of distance in that direction is rho d theta, so that would be rho, but quantity squared, so we get rho squared. And then z is already in units of distance, so that's our metric tensor. So the only thing in there that would ever show up in any of these derivatives is going to be a derivative. So everything's constant aside from this entry, the theta theta entry, and the only derivative that I can possibly take of that to get non-zero, because everything else is constant, is going to be a derivative with respect to rho. So this is why this is a calculus light but index heavy problem. So the only non-van component, and instead of using scripts 1, 2, and 3, I'll just call them rho, theta, and z, is going to be a term that looks like this. G theta theta derivative taken with respect to rho. Everything else is gone. If I take, d by d rho of g rho rho or g rho z or something like that, it's all going to be 0. So these are the only things that'll show up. So if I squint at this equation, what I realize is that, okay, the only things, therefore, that will show up are I need 2 thetas and I need a rho. 2 thetas in a row, 2 thetas in the row. So the only possible non-zero Christoffel symbols are going to look like this. They're going to be rho theta theta, theta rho theta, theta theta rho. And if you're clever, you can realize that a couple of these are going to be equal. If I just take some permutations in k and j, they're going to be equal. So these two things should be equal, but we'll just do them out longhand anyway for practice. So everything else has got to be 0. So for instance, if I had d rho zz, I'm going to at some point have a zz index which is constant, or a z rho index which is constant, and any derivatives of them whatsoever with respect to anything are gone. So we don't even care about those. So which one did we start with? Yeah, let's just start with this. And just take that really seriously. I have d, and then matching indices. I have rho theta, d theta, theta rho, d theta. I should always have 1 rho and 2 thetas, and then g theta theta rho, and that's my guy. So that I can examine or just recap the argument I just made is 0. That, looking at the metric tensor, or just recapping my argument is 0. And then this, g rho rho derivative with respect, or sorry, g theta theta derivative with respect to rho, this is equal to 2 rho. So I get minus 2 rho there, and then I get a 1/2 there, so this whole thing becomes minus rho. Okay, so same argument. We'll just skip there. This is going to turn out to be the exact same thing as it turns out, but I have a little bit of room here. So I have d g theta theta, derivative with respect to rho. Flip those, d g rho theta, derivative with respect to theta, and then plus dg theta rho, derivative with respect. And then again, examining the metric tensor, we're just looking at the line above, 0, 0, and then this becomes 2 rho, and then a 1/2. This gives me plus rho. And it turns out this is also plus rho. You can think about that as just a permutation of these two indices, which gives me 0 plus 0 versus 0 plus 0, or you can do it out longhand. So those are everything else vanishes. Literally every other gamma that's not in there vanishes too. So those are gone. So really this is it. These are the set of Christoffel symbols. Let's do a little bit of counting to make sure we understand exactly like what just happened. Okay, I look at a tensor, I look at a third rank tensor. Who cares if it's a covariant or contravariant indices? So that, those three of those. So there are 27 possibilities that this could I, J, and K. Rho, 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 theta, rho, rho, z, etc. Of the 27 symbols, all but 3 of them are 0. So in my final accounting, when I write down the entire answer, there should be 27 symbols that I fill into, maybe 3 by 3 matrices was the suggestion for reporting your answer. 24 of them are 0, 3 of them are non-zero. We calculated 3 non-zero ones. So we'll just keep this in the memory bank for now. And the next question is, how do we raise an index? Because we computed this, but then we're asked for that. Very annoying of me to do that to you. So let's say that we want to raise an index, and I have gamma rho theta theta. I've got to raise and lower indices with the metric tensor. So I have this, right? In fact, I have all of these. And if I want to raise or lower an index, I'm going to need a dummy. So this is going to need a rho there, and we'll just put a k there, and we'll put a k there. So this gets Einstein summed over. I have a repeated index, 1 up and 1 down. So this is an implied sum over k. I have a rho upstairs, good. I have 2 thetas downstairs. So and remember, this is equal to sum k goes from 1 to 3, or k goes over rho theta and z. Okay. But then again, I know most of these are 0. So I'll write it out. This is g rho rho, gamma k, rho theta theta, plus g rho theta, gamma theta theta theta, and then g rho z, gamma z theta theta. Okay? So that's the Einstein summation, but this is 0 because we know it's 0, that's 0, we know that's 0. So the only thing that's non-zero is this, and we know what that is because we computed all the non-zero coefficients. So that's gamma rho rho, which is just 1. Don't even have to worry if we've got upstairs or downstairs, which I should have put on, should have put the indices on this, so I'll get that in a second. Yes, this is downstairs. We'll call this kj. Sure, kj is good. Doesn't matter if it's upstairs or downstairs, that's a 1, so that's 1 times this. So that means that gamma rho theta theta is equal to 1 times this, and that is equal to minus rho. Okay, we're going to have one of these, which is less obvious. And now I have to go back and look at my metric tensor. I want that. I want upstairs. This is the inverse tensor of that, which is to say the thing that when I multiply and sum over an index, I should get a delta function, which would mean this is h1, h2, h3, not to the second power squared, but to the negative 2 power. So this is 1, 0, 0, 0. Okay, writing it in a kind of goofy way just to make the point, 1 over rho squared, and then 0, 0, 1. And when I matrix multiply these, I get the Dirac Kronecker delta function. So I get Kronecker delta when I do these. So now for the second one of these that I compute, I do actually need to worry about what form of the metric tensor I was asked about. Okay, so I'll do this for theta rho theta, and that is going to be, we need a theta upstairs. We have a dummy index, we'll call it that we sum over, and then j, and then rho theta downstairs. And so that's g theta rho gamma rho rho theta plus g theta theta gamma theta rho theta. That's the thing that exists. And then finally plus g theta z gamma z rho theta. Same argument. This is nothing. This is nothing. Got a z there. We know it's definitely nothing. And then that's the thing that we computed, rho theta rho. That's 1 over rho. And then aha, 2 upstairs, that's 1 over rho squared. So that's 1 over rho squared times rho. So this whole thing equals 1 over rho. Okay. Okay, so we have one more of those. I'll just write it down. Need a bigger whiteboard for Christoffel symbols. You can show through the same argument that gamma last one, theta rho, you're not going to be surprised by this at all, is 1 over rho. You know, if you're good at symmetry, you can think about that as kind of an obvious consequence of just flipping those two kind of trivial indices, the second two indices. Okay, we worked for the ones with all covariant indices. We raised them the way that we're supposed to raise indices with the inverse metric tensor. And then we ended up with these three things. These three are non-zero. All of the other 27 total indices, so 24 zeros are, or 24 indices are 0. Okay, so the suggestion was you report your final answer, which should be 27 numbers, in the following way. So I have gamma rho, and then there's just, you know, call it ij. So this is a 3 by 3 matrix. And then I have one non-zero index, the minus rho. And that's in the theta theta position. And then everything else is 0. And then gamma theta upstairs, and then we have two indices downstairs, so another 3 by 3 matrix. Okay, this is more interesting. We have rho in the theta rho, sorry, you have a 1 over rho in the theta rho position. And then we have a 1 over rho in the rho theta position. And then everything else is zeros. And then this is the one that I could have done even without any of those shenanigans. Anything with a z is 0, so we get all sorts of zeros. Okay, and if you went on like Wolfram Math World or something like that, you should have seen the Christoffel symbols in this form, or potentially up to, I think maybe you can get a minus sign depending on a convention. Whether or not they put these upstairs or downstairs, there might be a rho upstairs or downstairs, power of rho. But this is, again, this is an exercise to learn stuff about how to work with tensors, namely the metric tensor and Einstein summation. And this is the basis of how you do calculus in curved coordinate systems. So, you know, I want to do calculus, but my x-axis isn't flat, it's wiggly. So I would use these in what's called the connection.